So far we have discussed in detail the reactivity of your N-pi star, and as well as we have studied reactivity of your pi star. Yes. So, and in that N-pi star reactivity we have seen several reactions under the scheme, and same way in pi star we also discussed about cis trans isomerization, we have discussed about dimerization of our alkenes. Okay. So, that two are the major reactions of your N-pi star and pi star reactivity. And now onwards we will take some selective chapters and we will discuss. Okay. In this class we will be trying to understand more about the photo rearrangements. Okay. So, we will start initially with di-pi-methane rearrangement, and then we slowly move to cyclohexanone rearrangements and there. So, today class we will be discussing on di-pi-methane rearrangement. Okay. People call this as even DPM as a salt as abbreviated form. Okay. Di-pi-methane rearrangement, or you call them as DPM. Okay. So, if you have a non-conjugated diene system, okay, you have a non-conjugated diene system separated by a sp3 carbon. Okay. That type of systems particularly give you di-pi-methane rearrangement. What I am exactly saying is that you have a, for example, so it is a non-conjugated system, okay. It is a diene, non-conjugated diene, and it is separated by a carbon which is sp3. Okay. This type of systems you can start observing di-pi-methane rearrangements. Most of this di-pi-methane rearrangement has been done by Zimmermann. Okay. So, people call them as Zimmermann di-pi-methane rearrangement. Okay, he has done a lot of contribution towards di-pi-methane rearrangement, Zimmermann. So, you can call them as Zimmermann di-pi-methane rearrangement. Okay. So, exactly what happens is that if you take a non-conjugated diene and if you photolyze, you get a product like this. Okay, and it's like it's the major product. It has been undergone some sort of rearrangement if you see the product. Okay. You can understand this mechanism in two ways, one happening from the singlet pi star, or it can also you can try to understand it from triplet pi star. Okay. So, we will see how it happens from singlet pi star if it happens. Okay. I am just writing the mechanism if it happens from the singlet state, okay, singlet of the pi star state. So, what is singlet pi star normally in alkenes? How it looks like? More like a deuterionic. Yes. So, I can say that it can be like this once I photolyze in the singlet excited state. Then what you can do? I can push this across. Can get this one. then I can move this system like this, okay. And then you can always have your cyclization. Okay. So, this happens from singlet state, the mechanism you can think, because we know that alkene in singlet state more exists like a zwitterionic. So, I can move with a plus or minus. Okay. The same mechanism you can also think if the reaction goes from the triplet pi star. What happens in triplet pi star? The whole chemistry, how it looks like in triplet pi star? It should be radical, right? Because singlet it will be zwitterionic, and in the triplet I can think this chemistry in by radical, right? Yeah, I can use some sensitizer. You know that directly photolysis is hard. So, I can do with respect to a sensitizer and take it to the triplet state, then it can be a radical chemistry. Okay. But most of the time di-pi-methane rearrangement are seen as radical chemistry, okay, not like zwitterionic. So, then what you can do? You can just combine this radical. Get this, what is this? Yeah, 1,4 diradical, that is a good driving force for this to happen. Can get nice 1,4 diradical. Okay, then I can cleave it. Okay. So, to give me a radical this, and you know isopropyl radicals are stable. Give me a. So, that is how you can look di-pi-methane rearrangement in two ways. The mechanism you can see it from singlet pi star, and you can also see the chemistry in triplet pi star. Singlet you do with more zwitterionic way, and in triplet you do more like a radical chemistry. Fine. Okay. This di-pi-methane rearrangement most of the time you can say that its substrate controls the di-pi-methane rearrangement, particularly the substituent at central carbon, okay. This and the substituent at the vinyl carbon they have a lot of control across your di-pi-methane rearrangement, okay. So, that part you should know, like I can say substituent at the central carbon substituent at the vinylic carbon. This has a lot of control across your di-pi-methane rearrangement. We will see one example, then you can understand what happens. See, I am taking a non-conjugated diene. Here my central carbon is not substituted, okay, it is just a hydrogen, 2 hydrogen. If you photolyze in presence of sensitizer, okay, so what do you expect? So, you should go by triplet radical chemistry. You get this one, okay. Then you say that yes, I can do my di-pi-methane rearrangement. All right. Then I can cleave this to get me a product like this. Okay. But if you do a thorough investigation of this reaction, okay, it does not go via this, it does not go via di-pi-methane rearrangement. You do not get this 1,4-diradical. Okay. But instead of that, what happens is, you get your 1,2 hydrogen shift nicely. Okay. Think of getting your 1,2 hydrogen shift, and this then cyclize, the product are same. Okay. This then cyclize to give me this, but this reaction does not go by di-pi-methane rearrangement, it goes more like a 1,2 hydrogen shift. See, that is why I am saying the substituent at the central carbon, yeah, in this case your product are same, but I will give you several examples in which the products will be different. Okay. So, the substituent at the central carbon has more saying or more control over your di-pi-methane rearrangement. So, you should think about whenever you see whether it is as a methyl or phenyl, then you think about your di-pi-methane rearrangement. Okay. In this case 1,2 hydrogen shift is much more facile to give you the product. So, we will take another case where like how the substituent at the vinyl carbon does not allow di-pi-methane rearrangement to occur. I have phenyl here. So, my substituent at the central carbon is fine, but if you see my substituent vinyl carbon is one side I have a methyl and other two side I have a phenyl. Okay. Now, if photolize in presence of sensitizer, so what you can think about? You can excite depending upon your wavelength, you can excite this end or you can excite this end. Okay. Any guess? So, actually I should get like this if I think of a di-pi-methane rearrangement, right. So, you should, I can excite this end or this end. You can make a dot dot and then make a cyclization, or you make a dot and make a cyclization. You end up your 1,4 diradical, right. Now, I can cleave this. Okay. To get me this product, yes, right, fine. But what happens in this reaction is that what do you think, there can be any, so you get this product, but very minor, but you get another major reaction happening in this case. Huh? Yeah, that is fine, but the 1,4 diradical itself is not formed. It does not go this pathway at all. See what happens if I photolize this, get a radical like this, right. So, what you know, this can undergo, this is called as free rotor chemistry. Okay. This particular bond can rotate like this, very free rotor. Okay. Just deactivate all of your di-pi-methane product. This is called as free rotor chemistry. this keep on happening. So, it can go from cis to trans, and then so this chemistry happens. This is called free rotor chemistry. Okay. This free rotation occurs nicely. So, thus you can see substituent at your vinyl carbon also has some control across your di-pi-methane rearrangement. So, you have to, when you are thinking about di-pi-methane rearrangement, so you have to check whether your central carbon is good, okay, as well as your vinyl carbons are good before doing a di-pi-methane rearrangement. Clear? Now, we will see some examples of di-pi-methane rearrangement. This molecule. So, you think like which reaction will be there? Yeah, this will go completely di-pi-methane rearrangement. You will get 100% product. Okay, just write the chemistry by yourself. So, you get a 1,4 diradical, then I can cleave it nice. So, this product is the another major product in this chemistry. Okay. So, we will take next example and see what happens there. Done. Finished. Okay. Take a system where now my both of your alkene substitution is not same, they are different. This side I have a phenyl phenyl and this side I have ethyl and methyl. So, here it is not like a simple di-pi-methane reaction. So, if I photolyze this, again you will say, yeah, you will get your 1,4 diradical. You get this, right. Now, I can think of cleaving it in two ways. I can cleave this direction, okay, and call it as A. I can cleave this direction and call it as B. Okay. So, we will write both the products and see what chemistry it gets you. If I cleave on A side, I get this radical. Okay. If I cleave A, if I cleave on the B side, I get this. So, this can cyclize this can cyclize to give me So, you can think about two possibilities. So, which will be then major? You want to break your A, or your product A will be major, or product B will be major? A, right? Because if you go back and see the radical stability, okay, this radical is much stable compared to your this radical, because it has a diphenyl, right?
Sir, but in the case of B, the double bond is more conjugated.
Yeah, but you get the product, na? But you see the radical first initially itself. Okay, once you get the radical, then only. So, this radical is much more precise. So, it gets stability of the radical and gives you the product. So, actually, if you do the reaction, this is the sole product. You get only one product. This is the only one product. Okay. So, that is why radical stability, once you know that, you are fine with it.
So, this experiment has been done by varying the temperature.
This particular experiment, why temperature you think any? Because we are doing in photolysis.
So, if reaction is done in higher temperature, B should be the.
See, normally what happens when you do photolysis, you never take it to higher temperature. That is one of the criteria you keep, because then it become more like a thermal pericyclic type of reactions, right. So, you keep it in the room temperature, maximum below the room temperature, and do the. Yeah, once you change the temperature, yeah, eventually things will change. But since you do photolysis, it's better that you are subject your reaction only to the light, not to the heat. Okay, now I will give this example. We will check how you guys can think about it. So, this on photolysis, you are going to excite only your alkene. Okay. So, that is fine. So, then what happens? You want to do your di-pi-methane with this. Huh? Yeah. So, it happens like it does not do your di-pi here. It mostly what it does a 1,2 hydrogen shift. See, that is what I say, like you think about always the competitive reaction. So, you can have your 1,2 hydrogen shift, then you can cyclize this, fine. These are some good reactions, you have to understand them. Okay. Same example, okay. I am taking the same example. Just same example, now I am putting 2 methyls, or even if you want reaction, see in methyl also you have this, but if you have 2 phenyls, okay. Then what do you think? If I photolyze, what do you think from here it will happen? Because previous case you said just 1,2 hydrogen shift, it is nice. In this case, it does NAS di-pi-methane rearrangement. Okay. Here which bond do you want to break? You have a choice here, you have an A and B. Yeah, because you want to get back your aromatization, right? Yeah. Penal substituted 1. So that's a care you have to take when you think about di-pi-methane rearrangement. Only you have to see whether once you get a radical, whether that radical undergoes any hydrogen shift, or if it doesn't undergo any hydrogen shift, then you can do your di-pi-methane rearrangement. Even sometimes you should look for cis trans isomerization is possible or not. Okay. So what's this compound? Barely. Yeah. We have studied this compound yesterday, previous class, right? Barely. There I just taught you that it is like a di-pi, it's like addition system. You can see now how it works by di-pi-methane. Okay. So what happens once you excite? See, these are the system nice to draw, like to understand your. Have a system like this. Once you get an alkene, right? You don't want to have addition across this. It's easier to have addition here. Get this. Now what to do? I don't want to break this bond because that is a newly formed bond. Otherwise, I will go back. Okay, right. So you have choice of breaking this bond. You have choice of breaking this. You have choice of breaking this. So you are going with choices. So which bond you want to break now? If I break this, yes, I will get back to my this one. Okay. If I break this one, I have always a nice system to make an again my alkene back, right? If I break this one, for example, and I will get a radical in that this position, which is again stable type of radical. Yeah. So you have a system like this, fine. Now you can join this. how it looks if you unfold it. Can you imagine unfolding this guy?
5-member ring with an upper one.
Yeah. If you want, we can try 1, 2. This, if you want to label like this, I am just labeling for your understanding. 4, 5, 6, 7, 8. Then if you say 7, 8. I just tell you how I have unfolded it. This is a nice example for di-pi-methane. These are the examples are even asked in your previous CSR. This not previous, like 2 years before. Barlin, di-pi-methane of your barlin. Okay. The only thing is that you should think that it is a di-pi system. Once you know di-pi system, yes, you can get this. But if you leave like this, it does not show. Okay, you have to take the product in this way. Like it's not like, it's more like a symmetrical. It's not an equation, more like a symmetrical of this. Right. So I want you to get this one. So that comes by. Clear? Shall we go for next example? This looks like more like a simple system. So you can you write the product directly without. What should your product? Can you write the product? Okay. Now I am saying like once you, because this type of rearrangements you can directly write. Okay, fine. Otherwise, yes, you get this, right? 1 for diradical. So which way you want to cleave? You have A and B. Which direction you want to cleave it? You want to cleave A or B? B, because your radical will be stable, this radical, right? If I cleave B, so this radical will be stable. That is why you are opening that. Right? Fine. Okay. These are some examples of your Aza, di-pi-methane rearrangement. Okay. Now we will go to another class of di-pi-methane rearrangement, that is you call it as Oxo Di-pi-methane rearrangement. Okay. Oxo Di-pi. Call as ODPM. Oxo Di-pi-methane rearrangement. It is more like your di-pi-methane, just in this case you will have your system with a ketone and an alkene. You get this nice system. See, this reaction, why it is important is that once you go for your natural products, like your most of your steroids or where you have a carbonyl system with an alpha beta enone and all this, they undergo nice Oxo Di-pi-methane rearrangement. Okay, we will see that example, but initially we will see what happens to oxide, how it works. So, it is similar like your, if you photolyze, you can photolyze your ketone, okay. Then you know that you are directly, you can go to your triplet, you can do singlet, then intersystem crossing to your triplet. So, then I can get my radical chemistry. So, I get this. Now, the advantage of Oxo Di-pi-methane rearrangement is that if you want to cleave, you have this two A and B, right. You can cleave this direction or you can cleave this direction. So, most of this case in Oxo Di-pi, it cleaves only on A, because it again can get back to its ketone. Okay. So, there will be no problem, then it will be only, most of the time it will be one side cleavage, because of the formation of your ketone. You get this product. Fine, looks to be simple. Okay, we'll do some examples on this. The cyclobutane system with your ketone. So, what product you can think of? So, I can get my excitation here to form a radical. Then you know that I can do a nice cyclization across this, possible. You have an O dot, you have a dot. Fine. So, I am just doing a cyclization here, this part, so that I get a radical and radical. Then you just cleave it off. You want to cleave this direction or this one. This one is better, right? So that I can get a ketone back. So, write the structure, just want to see how you write it. Just I am cleaving this direction, just write the structure, just want to see how you write it. Right? You can write like this. Any doubt? Okay. Now, we will take another which is now you take the system, you photolyze. Yeah, again this part you are clear, so that we will just write that part. Okay. Now what will happen? What you can think of? Yeah, it's again going to do di-pi-methane, okay, oxo di-pi-methane. So, I can take this radical, because always you cyclize, right, that is what you do in oxo di-pi. I can attach here or I can attach here, where you want to do. If I say 1, 2, 3, 4, you want to make ring closure to form like 1 and 3 or 1 and 4? 1 and why?
Radical allylic.
Yeah, because you get a radical which is allylic. Okay. Now, I can break this bond, right, because this is newly joined, I do not want to break that. I can break this one to get my ketone back, right. So, how it is done. One. Right, I can get this. Looks to be a very stable product. Fine. Because if you cleave here, it gives a nice 6-member ring. This one. Okay. Done. Okay. Now we will take one nice natural product. Right now, I am not fixing any stereochemistry. Okay, don't worry. So, I have this molecule. Okay. So, that is why Oxo Di-pi is famous, it is more interesting when you go for this type of systems, because you get natural products more like ketone with an alpha beta enone. This type of systems are very common in natural products. Okay. So, if I am exciting my ketone alone, see there are many chemistry. If I excite this enones, okay, that also you are going to see. Right now, I am going to excite my just ketone selectively. Okay. Then think about the chemistry. Without seeing the board, can you write by yourself? Just it should be an Oxo Di-pi-methane rearrangement. Then you can, once you finish the product, you can look and see that whether you are right or wrong. So, you get a radical. Yeah, that's that's why I said I am selectively exciting my ketone. There are many chemistry which happens from alpha beta enone. Okay, if I excite alpha beta enone, there are many chemistry.
It is only temperature variation.
No. See, alpha beta enone has different lambda max and ketone has different lambda max. Okay, because these are more conjugated ketones. So you can selectively excite your ketones. There are many filters you can do it. Fine. We can do next once we go there I will explain your cyclohexanone chemistry. There we will take the same example and see what happens if I excite this part. Okay. Right now we are exciting this ketone. So everyone got this one. Now what happens? This should be fine. This I think everyone would have got this one. After this, so after this your choices are to break the bond, right. So you can break this or this or this. That's the only 3 bonds you are. You don't want to break a newly formed bond. That's so you want to break this because you want to get a ketone back. Once you break this, become a radical. Okay, that radical can cyclize with this. Yeah. So then what you will get? So you get a 5-membered and a 6-membered one. So say I am not fixed your stereochemistry here. If I fix your methyl, okay, if I fix your stereochemistry of your methyl like this, then the things becomes little bit more interesting. Okay. So once it flips, what will happen? Yeah, then you should be taking that care. It will be other way around. Okay. So that's why in this example I didn't fix the stereochemistry. I was just want to find out the first the product. Okay. Then in later on I will ask you how to fix the stereochemistry and then flip it across. Okay. That will be much more interesting. And the one thing, this reaction sometimes goes by radical. Okay. If you use sensitizer, then your stereochemistry will not be that much. Okay. But if it goes by directly, like singlet statement, then your stereochemistry most of the time is preserved. That's all you should understand. Fine. Okay, this is on Oxo Di-pi-methane rearrangement. Okay. So another class of di-pi-methane is Aza Di-pi-methane rearrangement, which you have to. There is another. So you have a di-pi-methane rearrangement, you have Oxo Di-pi-methane rearrangement, you have Aza Di-pi-methane rearrangement. Because we never once nitrogen comes into the picture, you never think about di-pi-methane rearrangement. Okay. So it's better you should know that this chemistry happens even from the nitrogen here. Okay. Now you fertilize this. So you can get your 1,4 diradical like in the previous case. So, that you can get very well. Now, what happens? Because in Oxo Di-pi-methane rearrangement your cleavage was easier, because you want to get most of the time your ketone back, right. In this case I have a choice of, because newly bond I do not want to, I can cleave this one, okay. I have a choice of cleaving this, again I have a choice of cleaving this, right. So, shall we write both the products and see? If I cleave on A, sorry, this should be B. Get this, if I cleave on other way, nitrogen, phenyl, get your get this one. This can cyclize, and this, you get this both the products, okay. So, which you think like much more favorable? If you see the radicals, right. So, your B should be much more favorable, but it does not mean that you do not get A, okay. You get A also, that is where in Aza Di-pi-methane. Oxo and other di-pi-methane, most of the case you get sole product like main products, okay. But in Aza Di-pi-methane you get like both the products, okay. But this gets more favorable, that is fine.
If one more pH will be on the left side, then how does it become later?
Where which side?
4 pH groups are there. Right?
One phenyl, one phenyl, one phenyl. You want another phenyl here? Yeah. Then what happens? Then you should get both the products. No? Stability will be same. So, in Aza Di-pi-methane that's the thing. Like you get most of the time like more than one products. Now Oxo you get only one.
At that time you can consider that CC bond energy and CN bond energy.
Yeah, sure. Yes, you can do that. But yeah, you will always not end up like 50-50. You get 60 and 40%. Then that will come into the picture. Okay, that's good. So next class I will take some example on Aza Di-pi-methane. Then we will start doing other rearrangements like cyclohexanone rearrangements, and we have a lot of rearrangements to discuss. Okay, so we will end up the class with this.